So let's continue. I hope you can still see my screen. Hello?
Yes, you can.
Good. Yeah. So the first example is show that the function w equals to f of z, e raised to power z, is analytic in the entire complex plane. So it's simply to show that the CREs are satisfied and all the partial derivatives of u with respect to x and y are continuous functions in the complex plane. So solution, we know that z is always given by x plus iy. This is how we write any complex number. So w, which is f of z, will be the same as e raised power z, which is the same as e raised power x plus iy. So just by replacing z for x plus iy. Then from loss of indices, this can be written as e raised power x times e raised power y. But also by Euler's identity, we know that so Euler's identity or relation, e power theta I is the same as cosine of theta plus I sine theta. So that tells us that e raised power iy can be written as so what will be the value of e raised power iy? How can you write that function, this part, as in the definition of the Euler's relation? What is the value of e raised power I theta or theta I or theta y? E raised power I y can be written as my question is, how can we rewrite this part using this relation?
Y plus I sine y.
Correct. So we'll have cos y plus I sine y. So then now I can write this one as w f of z is the same as e raised power x cos of y plus I e raised power x sine of y. So this follows that what is the value of u? What is u? Remember, by definition, w equals to f of z equals to u plus iv. So what is u?
E raised to x cos y.
Correct. And then v?
E power x sine y.
Correct. E x sine y. So then now, let's get partial u, partial x. What do you get in this case? So it's just now a question of differentiation, nothing else. Differentiate.
Negative.
When you differentiate u with respect to x, negative
EX and Y.
when you differentiate u with respect to x, e raised to x cos y. Because the only part in what matters in the differentiation is the exponential, which has an x. And when you differentiate an exponential, it doesn't change. And then what is partial u, partial y? Partial u, partial y? Sure. What is the derivative of cos y with respect to y? Yeah, so negative ex sin y. And what is partial v, partial x? E raised to x sin y. And what is partial v, partial y? E raised to x cos y, correct. Now, clearly, partial u, partial x is the same as e raised power x cos y, which is the same as partial v, partial y. And partial u, partial y is the same as negative e raised power x sin y, which is the same as negative of partial v, partial x. So since the CR is IE partial u, partial x equals to partial v, partial y, and partial u, partial y equals to negative partial v, partial x, and partial u, partial x, partial u, partial y, partial v, partial x, and partial v, partial y. So here, this and these are satisfied. Are continuous functions. Then f of z equals to e raised power z is analytic in the whole plane. So the first thing is that the Cauchy-Riemann equations are satisfied. Then the second equation, the second condition is that clearly when you see those functions, exponential times trigonometric sine and trigonometric functions, cosine and sine, all of them are continuous functions in the complex plane. So the function satisfying the Cauchy-Riemann's equations and that aspect of all the partial derivatives being continuous makes us to conclude that the given function is analytic in the whole complex plane. So we get 2 or 3 marks. Then example 2. Is there at least one point or is there any point in the whole plane where the function f of z equals to z times conjugate of z is analytic? So is there any point, or at least one point, in the whole complex plane or domain where the function f of z given by z times its conjugate is analytic? So the first step is always to change z, and then from there you identify your u and v functions. So solution, we know that z is x plus iy, which implies, so if z is x plus iy, what would be the conjugate of z?
X minus iy.
X minus iy, correct. So that's by definition. So then now this will mean the given function f of z, z times conjugate of z, will be x plus iy times x minus iy. So can you expand and tell me what will be a real part of this complex number or complex function? So the real part will be having which function? So expand and then collect terms with the i's and then terms without i's, and tell me which part will form the non-I or non-imaginary part. So the real part after expanding will be? Please participate. What are really part of this function f of z? X squared plus y. You know, you are the only hope of your village. So don't let them down. So what we are doing, what is happening here that x multiplies, so x multiply x minus iy plus iy multiplied by x minus iy. So x by x is x squared, x by minus iy is minus xyi, iy times x, the same as plus xyi, minus plus I times minus I is minus I squared, which is actually plus 1. Y times y is y squared. So this will be plus just y squared. So we'll have x squared plus y squared, and then just plus 0i. Plus minus xyi plus xyi is 0. So this implies that our u function is
plus y squared.
x squared plus y squared, and then a v will be 0. So we remember that the Cauchy-Riemann equations, the starting point for this function to be analytic at any point is that it must satisfy the Cauchy-Riemann equations. So we have partial u, partial x must be the same as partial v, partial y, and partial u, partial y, the same as negative partial v, partial x. This is the starting point. Condition 2, this is the first equation. And then the other thing to test is that all the functions are continuous. So what would be our partial u, partial x? Partial u, partial x? When you differentiate this function with respect to x, what do you get? Just 2x. So I'll have 2x. And then what is partial v, partial y? What then? 0. So because it's just a 0 function, so this will be 0. And what is partial u, partial y? Two y. So we'll have 2y. And what is partial v, partial x? 0. Correct. So remember, all the two conditions for the Cauchy-Riemann equations must be satisfied for us to say that any point is analytic. So this we expect this to be the same, and we expect this these two to be negative of each other. So which value of x and which value of y will satisfy both conditions? That the first equation of the CRE is satisfied, and the second equation also of the CREs are satisfied. For you to say that partial u, partial x must be equal to partial v, partial y, what's the value of x? X must be 0. So when you fix this x for 0, then you'll be sure that 2 times 0 is 0. So partial u, partial x will be 0, and partial v, partial y as given is 0. And then what value of y guarantees us to say that partial u, partial y is the same as negative partial v partial x. Which value of x make that condition to be true? Value of y?
0.
Still 0. So when y is 0, then that second condition will also be satisfied. So, and actually, those are the only values. Those are 0 for x, 0 for y are the only values that will satisfy both conditions, condition 1 and condition 2. So therefore, the CREs are satisfied only when x equals to y equals to 0. So the point, or the only point where f of z equals to z times z conjugate is analytic is the point 0, 0, i.e. f of z equals to z times z conjugate is differentiable at 1 point 0, 0 and nowhere analytic. So that's what we say. So when you are given another function, so also now as an exercise, you check using CREs. Find which of the following functions are analytic at least at 1 point. So the first one is f of z equals to 1 over z. B, f of z equals z squared times conjugate of z. F of z equals to z e power z. D, f of z equals to modulus of z times conjugate of z. And then lastly, E, f of z equals to sine z. So you also did Math 125 analytic geometry. So the CR is in polar form are partial U partial R equals to 1 over R partial V partial theta. And then the second one, partial U partial theta is the same as negative R partial V partial R. Get some time and prove this. And just remember that to transform from rectangular coordinates to polar coordinates, X is the same as R cos theta, and Y is the same as R sin theta. So using your knowledge in Math 125, the analytic geometry, then I should not have trouble to prove that. Then lastly, we define harmonic functions and give examples. So recall that. Okay, by the way, have you done vector analysis course? Have you done Math 313?
Personally, I'm not done.
But is there anyone in class who has done 313 vector analysis? George, have you done 313? Okay. Okay, yeah. So if you have done 313, then this is an obvious thing that you know. But anyway, even if you have not done, then it's not a hard concept to understand. So recall that we write this sign. Oh, good. So, or we write this. This is called Laplace operator. And Laplace operator in 2D means partial squared here, partial squared, partial y squared. In 3D, we write it as partial squared, partial x squared, plus partial squared, partial y squared, plus partial squared, partial z squared. So this is what we call the Laplace operator. So either use triangle or use this inverted triangle and square. So in 2D, we only have x and y. In 3D, we have x, y, and z. So if phi is a function, So case one, if phi is a function of x and y, then we write this partial squared phi, partial x squared, partial squared phi, partial y squared. And then two, if this phi depends on three variables x, y, and z, then we write partial squared phi, partial x squared, partial squared phi, partial y squared, partial squared phi, partial z squared. So these two are actually called the Laplace equations. So these two are called Laplace equations because actually applying the Laplace operator to the function phi. So if phi is depending on two variables x and y, then it will be Laplace in 2D. If phi depends on three variables, then it should be Laplace in 3D. So having known that, then we can define a harmonic function. And it has a pretty easy definition. It's simply a function that satisfies Laplace equation. So function phi is said to be harmonic in a domain D if in this domain it has continuous partial derivatives up to second order inclusive and satisfies the Laplace equation. So you equate this one to 0. Remember to equate this to 0 for it to be an equation. So that's the partial derivative of second partial derivative of phi with respect to x plus partial derivative of phi with respect to y equals to 0.